So this was a surprise to me too, and again, this only happens once you reach a certain eccentricity cutoff. Anything lower than 0.6, you don't see this. And all we changed in the simulation was eccentricities, nothing else. So what does this look like? This is in projection, and we're only plotting the perihelion position. If you plot a three-dimensional image of the structure, now this is idealized, and the colors don't mean anything, it's just to try and get a visualization. You see, you go from being something that was in the mid-plane, but instead of becoming a puffy torus, like we would understand with the low eccentricity systems, you get something that looks more like a cone shape. In this particular example, the perihelion positions or eccentricity vectors are pointing downwards. In the last example, they were all pointing upwards. It doesn't matter whether you go up or down, it's numerical noise. So it happens 50% of the time everything goes up, 50% of the time they decide to go downwards. Okay, so what is the question? Why? What are you doing? Why do you do this when you're highly eccentric? So Kepler elements are the worst way to explain what's going on here. So a much nicer way, because we're dealing with torics and vector quantities, is to look at an orbit and describe it in terms of its angular momentum vector J, that just points normal from the plane, and its eccentricity vector E, that gives you the orientation of the orbit in its plane. But I also like to use boats, so stay with me here. An orbit and a boat are very similar. So if you think of having a boat and having your orbit run like a rope on the outside of the boat, the mast is going to be your angular momentum vector, and the eccentricity vector is going to be pointing to the front of the boat. And someday I will learn the right words.
Bow.
Bow, thank you. So there are three rotations that are really intuitive to us, because we deal every day, or not at all, with boats. I would much prefer to deal with this stuff, but anyway. So you can pitch forward, okay, and so that is rotating over your minor axis in orbit terminology. You can roll over your major axis, and of course you can yaw, which is a word I've learned especially, which is redirecting your eccentricity vector, right? So I'll use that terminology to explain how does this weird orbit kind of clustering actually work. And I'm going to do it very simply with just two orbits within the disk. And so I'm going to set up the orbits as if they're two boats pointing at each other. I'm going to perturb one of the boats, or one of the orbits, and see how does that propagate to the boat that's directly across from it. And you'll see that the second boat reacts to reinforce that perturbation, and it's an instability that makes all the orbits rise in the same direction. Okay, so this is the most complicated slide, but it's very easy if you follow along. So I'm picturing that we have that axisymmetric distribution of eccentric orbits in a disk, but I'm picking out just two orbits. So one's the red orbit, and you'll see a blue orbit pop out in a moment. And initially, this orbit 1 is this black line drawn here with an angular momentum vector that points upwards, an eccentricity vector that points in this A direction. And what I'm going to do is perturb the orbit. I say, like, initially everything's totally flat. And if nothing perturbs this system, there would be no evolution up or down off the plane, right? But I'm going to perturb it with an impulsive force off the plane, either up here or I'd perturb it down here. It doesn't matter which way you do it. What is going to happen to orbit 1? So we can use these equations here. So the angular momentum vector of orbit 1, this is r cross v is in this direction to give you j up here. It's just like the right-hand rule. What is the torque that's going to act on this orbit because of this force? It's r cross f, right? So r cross f, if you use your right-hand rule, that means your torque is going to be going in this direction. And I've colored it in red because it means it's going to roll. So you've got an angular momentum vector. Torque is the rate of change of angular momentum. So you add those two vectors, and you get that resulting red angular momentum vector. So your orbit rolls. That's what orbit 1 does. We take away that impulsive force. We're done with it. That's all we wanted to do, just set it off, see what happens. And now we say, well, what's going to happen to orbit 2? Remember, orbit 2, I've just got facing orbit 1 across from it in the disk. It's this blue orbit. So initially, it has this orbit that's colored in a black line. And what is orbit 2 going to do to it? Well, orbit 2 has rolled, so it has created a force now that's lifted upwards in one direction and downwards in the other direction. So it's lifted up here, force in this direction, has a force exerted downwards in the opposite direction. So again, we can use these equations. R cross F for a torque. You do it on both sides. Part of the torque cancels. The part that does not cancel is in this direction, along this A direction. So we've got angular momentum vector, a torque. So our new angular momentum vector color-coded in blue because it's pitching orbit 2 forward. What does that do back to orbit 1? Well, the apocenter of orbit 2 has been pitched forward or lifted off the disk. So you've now got a net force that's directed upwards that you didn't have before. So you're reinforcing that perturbative force that set the whole thing going. And what that has done to our system, you've got one orbit rolling, one orbit pitching, and they're just going to keep doing that to each other. So that's just 2 orbits, but this is how we've explained what's going on in this system. We can jump to n-body simulations. This is a really busy plot. I'm not going to go through the whole thing to show you that all of the orbits in the disk take part in this. They all pitch forward and they all roll to the right. Or if your numerical noise started in a different direction, they all pitch backwards and they all roll to the left. All of them do this. You can see this if we look at their inclination. Remember, red is rolling and blue is pitching. These are, the strong lines are the mean or the median values of all of the orbits in the simulation. And then the shaded part is a standard deviation. And so you'll see they all gain this positive roll value. That means they all roll to the right in the same way. And they all pitch backward, or I don't know which one this is in this particular simulation. But they all do it. None of the orbits are allowed to go in the opposite direction. And this is why they all pitch in the same direction. They actually all roll either left or right in the same direction. This is why we called it the inclination instability. It's not obvious from this linear plot, but it's an exponential growth in inclinations. They grow extremely rapidly with an exponential timescale until they reach something like a radian, 60 degrees, and then it saturates. Okay, the other thing I want to point out is this omega as a function of time. I know this time is unitless. Bear with me, it's a secular thing, it's fine. What I want to show with this omega, this is a Kepler element that describes the orientation of an orbit. I won't go into exactly what that is in 3-dimensional space, but for low inclination values, you can very easily show that omega is given by how much you're pitching divided by how much you're rolling. So when all the orbits are pitching and rolling in exactly the same way, all their omega values collapse to a single value and last for a really long time scale. So this is going to be important where we compare it to simulations. Okay, the last thing I wanted to show is the eccentricity evolution. So if you start your simulation off with 0.9 eccentricity, so very high, all of these simulations are completely different from each other, but they all show the same qualitative behavior. As your inclinations grow, your eccentricity has to drop. And this is just conservation of angular momentum. If you've got angular momentum vector sticking up, you're an axisymmetric disk, you've got to conserve that angular momentum vector. So when you start lifting everything and angular momentum goes to the side, your magnitude of angular momentum has to increase. You have to get more circular, and all the orbits do that. This will be important again comparing to observations. So again, this is the mean value. There's a standard deviation. But all of the orbits drop in eccentricity as they incline.
It looks like it settles to where the threshold of instability is.
Yeah, so that is dependent on what your initial value is. Yes. Yeah.
Is that what saturates it in a sense, though, that they're becoming less eccentric as they're inclining?
I think it's more that they become so highly inclined that, you know, once you get to like an average of 60 degrees, the torques are completely different than at least what we were looking at in that 2-orbit model that's very simple, right? So I think the behavior has to change because you're no longer in a disk at all. And that exponential phase really lasts when you're at low inclination. Once you're at like 40, 50 degrees, you're really turning over quite quickly. Okay, so these dynamics was caused by just the collective gravity of all these small particles around a massive, more massive body. Causes exponential growth in inclinations. They all decrease in their eccentricities. This increases the perihelion distance of the bodies. So perihelion distance is the closest approach to the massive body. It's given by semi-major axis times 1 minus eccentricity. So if you drop your eccentricity, you actually increase the distance. So this is going to be important comparing to observations. And the last thing is that they cluster an argument of perihelion, which is just a Kepler element way of saying they're all pitching and rolling in the same direction. Okay, so now, observations.
Just a quick question.
Yeah.
So what sets the limiting eccentricity of this model? What sets E.7 as the limiting eccentricity? Is that kind of this prediction and pitch roll model that you've explained?
Yeah, so the limiting eccentricity we found is something more like 0.6. And it's really about the mass distribution in your orbit. So I could go back a few slides, but maybe I don't really need to. If you picture the 2-orbit model, I just put the force, a perturbative force, what happens at apocenter. And you all let me do that, right? Because I told you I would do this because, you know, it will take a long time for us to integrate around the orbit. But as you get